I started the recording.
Okay, so today I have the pleasure to invite Guilherme Franzmann from Stockholm University Department of Philosophy and NORDITA University to give a talk in our seminar. And he will be talking about the question on whether quantum subsystems are invariant. And yeah, the stage is yours. We're looking forward to your talk.
Okay, thank you. Thank you for the invitation. It's nice to be here, and it's also nice to be back giving online talks. So let's see if I still remember how to do this. So today I'm going to be talking about quantum subsystems, in particular in the context of gravitational quantum subsystems, and to which extent they are invariant under time evolution, but also in particularly under measurements. Most of the talk is going to be based on a paper put out recently, which is on the bottom corner of the page of the slides. So you can have a look on the paper later on. Also, I'm happy to keep it quite informal, so please ask any questions at any time. Depending on the nature of the question, I might queue it for later for the discussion part of the talk, just to not interrupt much the flow of the talk, but you can try your luck. Okay, so let's start by thinking about a mysterious box, actually. And so I want you to imagine that you go to your lab and you are a very good theoretical physicist and experimental physicist with a lot of experience in modeling quantum systems. And one day you go back to your lab and you find a black box in your lab and you try to open the box, but you don't manage it. But the box nonetheless has a display which shows the energy values that the system inside the box can take on. And so you start playing with the display and you start taking note of all the possible energy values, assuming that there is no energy degeneracies in the system. By knowing all the different energy values, arguably you know the size of the Hilbert space needed to model the physical system inside of the box. And given all your experience modeling physical systems, you decide to try your luck to see if you can actually figure out what's inside the box by modeling it and trying to reproduce the energy spectrum that you actually got by taking notes on the display on the box. And so you start to do something very simple. You decide to model maybe what's inside the box with spins, a chain of spins, a one-dimensional chain of spins. And in particular, you know what to do with different spin sites. For instance, you know that you can couple two neighboring spins. So for instance, here, they're coupled on the Z direction. So you have spin site 1 coupled with 2 with a coupling strength J. But also you could imagine that actually the different spin sites can be under the influence of some magnetic field. So here you imagine that there is an H magnetic field on the Z direction acting on spin site number 4, for instance. And so you have those Lego blocks to model your physical system. And then in the end, you decide to propose a model, which is this. You imagine that inside of the box, there are 4 different spin sites. They all have neighboring like couplings given by strength J on the Z direction. And they also have some external magnetic field H also on the Z direction. So you model the system like this, and you compute the energy spectrum, and it turns out that you find a unique value of both J and H that matches exactly all the energy spectra that you observed when you're playing with the display of the box. So what do you do? Of course, you're excited. When you're excited, you go out from your lab and you call a friend and you tell the story to your friend. You're like, there was this mysterious box in my lab. I decided to model with this chain of spins, and I computed the energy spectrum, and I found precisely the coupling and the magnetic field needed to reproduce the energy spectrum that I observed. And the model is this one. But before you do that, before you explain what's the model that you created to explain what's inside the box, your friend tells you to stop because they also want to try to model by themselves what's inside of the box. And so your friend now goes away from your lab, and decide to model by themselves what's inside of the box. And they have a similar idea. They also know the number of energy different values that the system can take on. So they also model with 4 spin sites. But you see that there's something different. Instead of like their neighboring coupling being J, they're using H, which was what you called your magnetic field. And for the magnetic field, there is 2 different contributions. There is a magnetic field on the X direction with strength J, and another magnetic field only on the spin site number 1 on the Z direction with value H. But nonetheless, your friend gets the same energy spectrum that you had obtained for that system. So of course, you start discussing what's going on. How can we understand what happened here? And then by talking to your friend, you realize that there is a way to uniquely relate your 2 different descriptions of that quantum system. And you basically come up with a table. And the table maybe looks a bit overwhelming at first. So let's just focus on 2 cases. So for instance, you realize that what your friend called the spin site number 4 on the Z direction corresponds to actually the product of all your different spin degrees of freedom on the X direction. Meanwhile, what you called to be a coupling between 2 neighboring spins on the Z direction is actually the degree of freedom associated with the X direction for the spin site in the description of your friend. And of course, so you can do this mapping between the 2 quantum descriptions, which are quite different because not only we're talking about different orientations, but the very notion of localization, or in this case, what you call a site, a spin site, is completely non-local, because you see here in this particular example, or in those 2 examples, even the number of spin sites which are related between those 2 different mappings, they're not the same anymore. Okay, so what's happening? So formally, this is called a duality. And probably many of you have encountered this before. In particular, if we were talking about n-dimensional systems or n-dimensional n sites inside of the box, those are the 2 different Hamiltonians you can write that are actually the same Hamiltonian, as long as you connect the U and S spin sites descriptions in this non-local fashion. So for instance, here you see that the UI site on the Z direction is actually a product of the spin sites on the X direction on the other description. Okay, so you understand that, but maybe you still want to ask the question, well, which one is it? How can we, is there a way to find out what is actually the physical system that is inside of the box, right? Now, typically, when we want to find out what's inside of the box, we try to hammer it. So that's pretty much what's happening when you go to CERN every day and people are literally like colliding quantum systems and trying to break them apart to see what is inside of it. The problem is, what if you cannot open the box, right? We just saw that each description of what's inside of the box, in principle, assumes a different notion of the systems. There's a different notion of which parts of the systems are interacting. And therefore, there's a different notion of even what's a neighboring site. So we already like seeing that the very notion of what we could understand as space or spatial distribution of physical systems inside of the box is not necessarily well-defined in this particular scenario where there is a duality. And the question is, how do we make sense of all of that? So to start to understand better what's happening, we're going to go back all the way to classical mechanics. And we're going to start from there and see if we learn a bit more what we mean really by a subsystem, by independence of subsystems, and how we can think of that in this quantum case. Okay. So let's start with classical mechanics. And in classical mechanics, typically what we see as a quantum system, if you open a textbook, initially is going to be basically a particle defined on phase space. And that, of course, is quickly generalized to have multiple particles, which are going to occupy a vector in phase space, which is basically all the positions and all the momenta of those particles. And then to talk about the physical characteristics of the system, typically we think about what we're going to be calling as observables also in quantum mechanics. But in the case of classical mechanics, initially, we tend to think of observables as basically real infinitely differentiable functions that takes points in phase space and bring it to real numbers. And so this is what actually defines the algebra in classical mechanics of our observables. So we now remind ourselves about what's a system. We have this idea of observables. There is also here the idea of a state to some extent, in the sense that each point in phase space is going to actually give potentially different value for the observables that we are considering, all those functions f. But in our attempt to go into quantum mechanics, but even in classical mechanics, when we want to think about statistical mechanics, we want to be more general about what we mean by states. And so typically what we want to think about state is actually as a linear functional that actually take those observables and spit out some value. And so typically, instead of thinking about every point in phase space, we actually have a distribution function defined on phase space, under which or with which we can define now what we call the expectation value of our observables. So in classical mechanics, for instance, would be something like this. Expectation value of some observable f, given some state w, is going to be the integration of this observable across the support of this particular distribution function associated with a state in your phase space. And so, of course, now not only we have those f functions, which are our observables, to be real and infinitely differentiable, but they also have to be measurable functions that are bounded. So the algebra becomes a bit more restricted in this context. And in this context, that we can recover this notion of state as a point in phase space, where we typically thinking about this distribution as basically a delta function. And those are what we actually mean by pure states in classical mechanics, as opposed to mixed states, which can be both discrete or continuous summations of those points in phase space. Okay, so we just recalled what is a system in classical mechanics, what are the observables, what are the states, and we're trying to set up the language, a common language that it can then later on translate also to quantum mechanics, quantum field theory, and canonical quantum gravity. But we still have to now analyze what we mean by subsystems. And this is when things start to become a bit trickier. So to talk about subsystem, we need to also talk about independence, because the only way we have to be talking meaningfully about how can we distinguish different parts of a given global system into its subparts. And typically there are two ways in which you can think about that. One is where you start with a global system here on the left. By the way, you can see my cursor, I suppose. Okay, so you have the global system on the left, and you can think about factorizing it, finding a way of like breaking that system apart such that the properties of the global system are preserved, now seen from the smaller parts of the system. Or we can think about composing smaller systems into a global system. And then we have to think about how can we compose in a meaningful way such that we preserve the properties of the subsystems, now seen from this global point of view. And to do that, as I mentioned, first of all, we have to be able to talk about what we mean by independent subsystems here. And it turns out that one way to think about this that is going to permeate the classical, the finite-dimensional quantum, the QFT, and also the quantum gravity potentially description of this factorization composition structure is going to rely on the idea of independent events. So basically, we want to be able to somehow talk about those expectation values that we saw just before, as if we can talk about them as a joint correlator that can be decomposed as single correlators for each subpart of our system. And so we want to find ways of decomposing the combination of both state and observables for our global system here on the left, understood now as actually products of combining observables and states of our subsystems themselves, such that the rule of typical probability of the independence of events is actually respected. Okay, let's see what happens when we try to do that. So let's step back. Let's imagine that we have a global system. We have a global phase space M. We have a set of observables F, and we have a state omega. And we want to think about computing this double or this two correlator, F1, F2, where the labels here, 1 and 2, we are already thinking that we would like to identify those observables with subsystem 1 and subsystem 2, even though here everything is still defined from the point of view of the global system. And so what we can think about doing is to first now find different states, say omega 1 and omega 2, that are going to be associated with each of those independent subsystems, and then see if we can rewrite this joint correlator as actually now single correlators where we have F1 only evaluated from the point of view of state W or omega 1 times F2 evaluated for omega 2. And the question is, can we do that? And how do we do that? So this would be the idea of like more factorizing. But then we can go back and also think about composing. So we could imagine that actually this global system is the result of somehow composing together two subsystems, each of their own now with their independent phase space, M1 and M2, their independent local algebra observables, which are going to be always having tilde on top of them, if you're not talking about the global system, with their particular states also defined from the point of view of this smaller phase space. And the idea is, can I actually now write this joint correlator from the point of view of the global phase space and the global observables as a product, all defined in terms of the smaller phase spaces associated with each subsystem. And the real question that we would like to address is, are those things all the same? So is it the case that I can relate a joint correlator from the point of view of the global system as rewritten in terms of products of single correlators also from the point of the global system, and also relate those single correlators which are global as written from the point of view of subsystems that would be defined completely independently, as if they were systems by themselves, and I don't have to refer to any kind of like global, all-encompassing system that they are part of. And so this is the kind of task that we want to address, because this is the kind of formula that we had before to discuss or to decompose joint probability distributions, as opposed to having the product of each of them for each independent measurement, if you will, for each subsystem. So can we do that? Well, we can. I won't go into details. And so you can kind of ignore the more technical aspects here. I just want to say that in classical mechanics, we do that all the time. And we do that by using or by invoking the Cartesian product. And so by using the Cartesian product, we have a way of not only combining subsystems into bigger systems and also factorizing them, but also relating in an isomorphic way the algebra of subsystems defined from the point of view of their smaller phase spaces with the algebra of them as seen from the point of view of the global phase space. And so by having the Cartesian product, there is a way of separating the global algebra into products of smaller algebras associated with each subsystem, and therefore define a notion of subsystem in classical mechanics, and then being able to write down joint correlators like this, such that we recover this idea of independence that we have already in probability theory. So we instantiate that notion of being able to do independent measurements in classical mechanics through the Cartesian product. And now the question is, can we do that for quantum mechanics? Can we do that for quantum field theory? And can we do that for quantum gravity in general? So before we go and talk about quantum mechanics, in particular in this context, I want to first highlight the fact that there is a way that space hides in quantum mechanics. So even though we could think of this austere minimalist description of having just a Hilbert space, having a wave function, wave vector, and having the Schrodinger equation, it turns out that the way that we typically do quantum mechanics, somehow space is actually there as well. So let's see why that's the case and how that happens. So going back to our Mysterio box, we saw that the box somehow illustrated the fact that quantum systems only described by our global Hilbert space, by state, and by Hamiltonian, wasn't enough really to characterize the classical properties of the system, such as what we mean by a site, a location space. And this is kind of puzzling, as I was trying to highlight in the beginning, because typically what happens is different. Quite often, we actually impart our classical notions of location into our quantum mechanical descriptions. So for example, if I go to my lab and I start building a Heisenberg chain of spins, basically for every spin site located at a given position I, for instance, I will typically write down that there is a C2 Hilbert space factor associated with that site, such that the global Hilbert space is just a tensor product of all the independent Hilbert space associated with each spin site. And this is really the general attitude that we typically impose when we do quantum mechanics in the lab, or when we try to model quantum systems in general. Typically, we assign a Hilbert space associated with a system to each classical subsystem, which is quite often in a given spatial or more generally space-time region. Therefore, some notion of space, or at the very least some notion of location in space, seems to leak into our quantum mechanical descriptions. And we can make that even more explicit to see really how that appears. Okay. So to make that more explicit, let's go back to our lab. Let's imagine that we have now an extended quantum mechanical system, which is divided into parts, A and B, which has a global Hilbert space H. So this is the typical setting of when people talk about Alice and Bob, so on and so forth. But really, any quantum system which is extended in space, in principle, falls into this category. So now imagine that each part is surrounded by measuring devices. So we have system A and B, and each of them have their set of observables, which are basically modeling all the different devices that we have around the quantum system that can make measurements. And also imagine that you have a clock fixed against the wall. So you actually set up a reference frame for the entire lab, such that for every second of the clock, any measurements that you do simultaneously on that reference frame, they actually shouldn't affect one another because they are space-like separated. So this is what we, of course, call macrocausality in this setting. And so essentially what we want to do, we want to aim to ensure that the statistics of those different parts are independent. And so now we are trying to operationally impose macrocausality such that whatever are the statistics coming from system A, they should not depend on the statistics coming from system B, as long as the measurements they are taken within a delta T, such that there is no communication between the two systems. So if we impose that, let's see what happens. So imagine that you have two measurements, one in each part of the system, and they define two space-time events that are space-like separated. Once you do that, you could imagine that either you have the original state rho, or you can have the updated state rho prime, in which one or the other measurement has already been taken place from your lab reference frame. But as I said, you don't want the statistics to be changed. So if I'm looking to system A and system B has been measured somehow, I of course don't want that to actually interfere with the statistics of my measurements in A. And so if I consider either the state originally rho or the updated state rho prime that came after measurement B was realized, I want the expectation value to be the same. So trace rho OA should be equal to trace rho prime O prime. And so if you impose that for a generic state and for any particular observable A, and the same for B, you can show that this is possible if and only if the observables in A and in B, they commute. So I'm just like, this is all, I mean, it's something that we always take for granted, but I'm just saying that this is directly connected to the notion of macrocausality. And so we see that the requirement that OA and OB commute has to do with the fact that we are considering the measurements to be always space-like separated. And so now we go from macrocausality, which was implemented in an operational fashion by saying that the statistics should be independent, to the notion of microcausality, in which the observables should commute when defined for each of those different systems. Now, why I'm telling you this? I'm telling you this because it turns out that when you have a finite-dimensional Hilbert space H, and you have a collection of subalgebras of observables which correspond to each different quantum subsystem, if they satisfy those three properties, which are they are local accessible. So each set of observables, they correspond to some controllable observables for each different quantum system. If they commute, which is just the thing that we just defined, that is our notion of operational macrocausality. And by bringing together the minimal inclusion of all those different observables for all those different systems, you actually recover the full algebra of the operators defined on the global Hilbert space. If you have those three different properties, that's the same as actually defining a tensor product structure. So what's a tensor product structure? Tensor product structure tau of Hilbert space H is an equivalence class of isomorphism. So you're factorizing your Hilbert space, and you assume that you have a well-defined TPS as long as all the different possible mappings that you can do to factorize your Hilbert space, say take T1 and T2, they're going to be part of the same class of isomorphism, as long as the product of one of these mappings with the inverse can always be written as a local product of unitaries or permutation of subsystems. So maybe it's too much of a definition, but the point is to say that now we see that actually the idea of having a tensor product structure that we typically take for granted whenever we see system A, system B, we write a state for A, state for B. Having this idea that you can factorize the Hilbert space such that you can talk about system A, B, C, and so on and so forth is actually relying on those three different properties. And one of them, as I said, is directly connected to the idea of having space-like events representing the measurements that you can perform independently on those different systems A and B and C and so on and so forth. But okay, so assuming that you do have this structure, then you derive the tensor product structure. And once you do that, this is the analog of our Cartesian product in classical mechanics. And so suddenly we can fill in the second part of our table. And so what we had for classical mechanics can also then be obtained for quantum mechanics. And so you can go from joint observables defined on the full global Hilbert space associated with a full quantum system. And you can actually see that as if you're talking about the observables and the states defined on the factors of Hilbert space, as opposed to the full Hilbert space. And so now the natural question is, can we also do that for QFT? The main assumption I had before in the previous slide was that we're still talking about finite-dimensional Hilbert spaces. Okay, so let's move on to QFT and see what happens there. So to give the intuition about QFT, we're going to take a toy model, the simplest toy model that we can think of, which is also interesting because we want to bring on gauge theories. And we're going to think about QED coupled with a scalar field. Okay, so let's start by writing the Lagrangian. So we have our QED Lagrangian. The first term is our free Maxwell term. We have our gauge fixing term. We have our covariant derivative of the scalar field and some mass term for the scalar field. So this is a gauge theory. The vector potential is transforms under gauge transformations. The scalar field is charged under this gauge symmetry, so it also transforms. And now you could imagine, following our prescription of what we did so far, we want to find the algebra associated with our scalar field so that we can talk meaningfully about independent regions of the field, so that you can think about field in some position X and field in some position Y as if they are independent from one another. And we, again, rely or fall back into the idea of macrocausality, but now instantiated as microcausality. And that's usually what we do in QFT, right? We open a book in QFT and you see that if the field is being measured in space-like separated regions, say X and Y, it commutes. And then you'd expect that you can use that to recover all the same structure that we just talked about so far. But things become a bit more complicated because, well, even though we do have this commutation relationship here for space-like events, again, being instantiated, it turns out that this is not gauge-invariant. And so these phi observables wouldn't be automatically what we would like to think of our observables to be associated with our measurements, as we just did before, because we like to think that our measurements in the lab, they correspond to observables which are gauge invariant. And the question is, can we find other sets of observables associated with the scalar field that not only satisfies this microcausality relationship, but they're also gauge invariant? And you can. So there is a whole literature on this. This is called dressing. You can talk about dress operators. There are many different ways of talking about dressing observables in QFT. The main message is to say that basically in Yang-Mills theories, generally speaking, you can always find a way of dressing your field such that you can define an observable, which is going to be gauge invariant and is going to satisfy some notion of microcausality that would allow you to fall back into the ideas that we had before on finite-dimensional quantum mechanics, and would allow you to talk about systems or regional spacetime in which those fields or those dress observables can be seen as independent. Here, one example is, this is a Wilson line connecting two different excitations of the scalar field, one antiparticle and one particle of the scalar field. And the key aspect here that I want you to highlight is that this dress observable is actually defined through an integration here of the gauge field. So in a particular direction. The details are not so important now. We can go back to them if you want later. The point is to say that if you define observables like that in scalar QED, then if you have X and Y on a small region of space-time, and you have some Z and W in another region of space-time, and those two regions are space-like separated, these D observables, they are actually going to be, they actually satisfy all the properties that we want them to satisfy to talk about independence of this scalar field on those regions. And so by doing that, actually, we satisfy the first property that is needed in QFT for us to have a notion of separability and therefore a notion of subsystem. So here we're back to this more technical table, and we don't have to go into all the details. We already saw how things work for classical mechanics and quantum mechanics in the finite-dimensional case. In QFT, things become a bit more complicated because not only you need this notion of Einstein separability or microcausality on your algebra of observables, but also you need something else, which is called the split property. And when those two things are combined, that then you can go from thinking about your algebras to actually being able to talk about Hilbert space being factorized. So here, the algebras can already be seen as somehow factorized, but that doesn't mean that you have associated with them a Hilbert space that actually can be defined locally for a region U and a region V, which are space-like separated. So in QFT, you need this extra property, and we can talk more about that later on as well. What I want to emphasize here is the fact that in principle, in QFT, without gravity, there is a way of also recovering a similar notion as what we had before. And therefore, the intuition of independence of events that we had before coming from probability can actually be instantiated at all those different levels. And there is a clear notion of how to think about subsystems being independent in classical mechanics with the Cartesian product, in quantum mechanics with the tensor product structure, and in quantum field theory when you have this microcausality of your algebra of observables, and also this split property that I'm not discussing so much about it. Okay, so that's kind of like the whole introduction of the talk before we go into the more, what I consider to be more interesting aspects of the talk. So before I go and start talking about why I care about this or why we should care about this, maybe I can ask if there is any question. Okay. So if there are no questions, let me continue. So to kind of like honor my background in theoretical cosmology, the first reason why I care about this is because when we look to the sky, we see that we have this cosmic microwave background. Probably most of you have heard about this before. So there is this radiation mapping of the sky, which corresponds to a radiation of temperature more or less 2.7 Kelvin. All these blue and red dots, they represent fluctuations of order 10 to the -5 in the temperature. And basically, this is a snapshot of how the universe looked like when it was around 380,000 years old. And most of what we do in theoretical cosmology nowadays, especially early universe cosmology, is really trying to understand how this snapshot of the universe can be mapped into the structures that we have in the sky nowadays, and also understanding what could have happened before these snapshots, such that this was actually yielded, produced back in the day. Now, this is interesting because this is a mapping of the whole night sky, right? So you put a satellite on the sky and you cover all the solid angle possibly. And so you have this mapping. And it turns out that just, for instance, if you take two extreme regions of the South Pole and North Pole, we know that if we call those regions U and V, they are actually space-like separated if we don't assume any exotic physics happening in the early universe. So if you just take standard cosmological model evolution for the universe and we go backward in time, we know that those regions were causally disconnected, unless we impose something funny, such as inflation, for instance, happening in the early universe. So that means that, in principle, we would like to say, okay, so those two regions are space-like separated. I could imagine that there is an algebra of observables that I can define when I look to this region of sky or when I look to the other region of sky, and they should commute with one another. And so I would like to model this whole setup as if those operators associated with those different regions that correspond to the measurements I can make when I look to the night sky, they actually commute. But the question is this true? Can we think of this being the case in the context in which we have a quantum field theory defined on a curved background, or in particular, if we are invoking some sort of like quantum gravity description to explain what was unfolding back in the day to define or to provide this particular image of the sky. That's our first context. Second context comes much more recently, in the last decade or so, or even less than 10 years. People have been advocating quite strongly for gravitationally induced entanglement as a way to probe the quantum nature of gravity. So there are two seminal papers, one by Bose et al. And Marletto Vedral. This is from Bose's paper, and the typical setup, if you haven't seen this before, you basically imagine that you have two masses, and each of them are actually in superimposed states, and you let the whole system evolve by only interacting gravitationally. And you see that because all the distance between every two possible combination of those two masses, they correspond to different distances in your Newtonian potential. This leads to a different Hamiltonian interaction for each of those possible branches of the system evolving over time, which leads to a different phase. And therefore, if the system starts in a product state of those masses which are superimposed, at the end of the experiment, this whole system becomes entangled. And then there is a theorem basically says that this is only possible, we can only witness entanglement by the end of the experiment if the mediator interaction that's actually combined or that's ruling the dynamics of those different possible branches of those different masses is actually a quantum mediator. That means if you open up Bose's paper and you see the mathematical description, this is basically what's written. You have some initial state, which is a product state of the mass on the left, superimposed between left and right, times the state of the mass on the second mass, also superimposed between left and right. And after some time, the system evolves such that now you have a global phase, and then you have different phases correspond to each of the different branches of the global state. And the final state is not anymore a product state, it would be an entangled state with different phases for each branch. Crucial here is that there are two assumptions. There is the first assumption in which you can write down a product state for the two masses, and that the initial state, not only there is the fact that you have a tensor product structure, that you can actually have factoring Hilbert space for mass 1 and for mass 2, but also on top of that, that you have accessible to you a product state as your initial state for the whole evolution of the system. So there's two different notions of independence here. One in terms of factorizing the Hilbert space, and the second one in terms of being able to write down a product state for the for combining system 1 and system 2. Now, so we have first the cosmological motivation. Now we have this more contemporary tabletop gravitationally induced experiments as a second motivation. And despite some level of contention, those arguably are examples of low energy quantum gravity phenomenology. So cosmological perturbations in the early universe are typically defined in terms of the matter and geometrical degrees of freedom, while those GIE experiments, they're typically locally modeled in terms of exchange of gravitational quanta. And so we seem to be in a context in which we need to be able to talk meaningfully about systems in plural that are somehow independent. You have this idea of factorizing Hilbert space or having a product state in a context where we have both gravity and quantum mechanics playing a role in your dynamics of the whole system. And the question is, how do we do that? Do we even know how to do that? So let's start with an example again. Let's go back and try to model low energy quantum gravity by just coupling with a scalar field. And let's see if we can do the same as we did for QED before. Remember that everything worked out fine in the end. Well, you start by writing down your Einstein-Hilbert Lagrangian, and then you couple with a scalar field. And then again, you can now go to the linear, to the perturbative level at the linear level of the theory. And then you see that your theory had some diffeomorphism invariance, which means that your metric transforms under linear diffs. Your scalar field also transforms under linear diffs. And so we have the same kind of issue as we had before. We wanted maybe to consider the scalar field at space-like separated distances to define our set of commuting observables, but they're not gauge-invariant. And the question is, can we again do addressing such that we can define meaningfully those sets of commuting subalgebras to talk about subsystems as being independent? And it turns out that this is not possible. This is not viable. Crucial here is that there are different, again, ways of dressing. Here is one particular type of dressing, but this applies to other dressings as well. What's important is that if you remember before, we had the integration of the gauge field, right? To define the dressing. And here again, you have to have the integration of the gauge field to define the dressing, such that you can define gauge-invariant observables. But the gauge field in GR is not the metric, it's a connection. And so you see that now you have those extra contributions. You see you have the integration of the metric here, which is similar to the integration that we had for the gauge field before, but also you have this in term, which has a derivative of the metric. And so this is gonna be a bit of a pain for us, and we're gonna come back to that later.
So Guilherme, so this is simply something like the integral of the Christoffel symbols along the curve. Is this the way to understand it? Okay.
Yes, precisely. So typically, the dressings can change dramatically because of the boundary conditions, but the general recipe is that there's going to be an integration of the connection. So if it's gauge theory, if it's GR, it doesn't matter. It's going to be the connection there. It just that turns out that the connection for GR is not the metric, and we have to now then somehow think of why that's the case and what can we do about it in this context. So in gravity, this algebraic approach is in principle obstructed, because now these dressed observables, even though they can be made into gauge-invariant observables, suddenly they violate microcausality. So they do not commute anymore at space-like separated regions. Now people talk about different intuitions behind that. Usually they say that different than in QED, if you remember in QED, a kind of like couple apart with an antiparticle. So of course, if you see from far away, the field has been screened away. Now in gravity, there is no anti-Poincare charge somehow. So everything gravitates. And so the physical intuition is that there is no way to screen a gravitational charge. And that's why physically, this is the reason why things are breaking down. Also, I just want to flag the fact that we are relying only on those local symmetries to make this argument. And we're only talking about the linear level of the theory. So you could imagine that any diff-invariant theory, in particular, any quantum gravity theory that recovers GR at the linear level will face the same challenge. So this is not just a generic factor, oh, we're doing low energy quantum gravity and maybe that's wrong or whatever. It turns out that anything that we do in terms of quantum gravity that falls back into GR, and we try to think of GR as an effective field theory that we can quantize, is going to have this problem. And so I would claim that this is a very foundational thing to be investigated further in the future to understand better what's going on. Now, back to the Felix question, really what I was trying to say before was that typically there is this V, this functional that appears on the dressing. And typically it is going to be defined in terms of this arbitrary integration of the connection of your theory. But for normal gauge symmetries, we do quantize the connection. While for low energy canonical quantum gravity, we quantize the metric, not the connection. And so that's why we have a problem, because suddenly this dressed observable, it has derivatives of the connection and the connection in its definition. And so when you try now to calculate the commutation relationship of this dressed observable in the case of gravity, at some point, you're not going to be only hitting the metric with the metric itself, but that's going to be the metric with derivatives of the metric. And that's going to give contributions which are going to be non-zero for the commutator. And that's why microcausality is in principle violated in those scenarios. And this is, you can actually, we're writing a review about this right now, also exploring this situation in other contexts. So this is going to come up probably later this year. But you can go back to papers by Giddings and Donnelly, 2015, 16, where those calculations are made very explicit as well. Now, the point is that, as I said before, from an EFT perspective, we do live in a regime in which low energy quantum gravity applies. As Rovelli says in this paper, or I think it's a book, bars and clocks are the tools that measure the line element, thanks to their coupling to the gravitational field. So unavoidably, we seem to be in this regime in which this typical formalism does not seem to quite work well. And so this notion of separability or notion of subsystem, at least in this regime, and given our understanding of low energy quantum gravity as an effective field theory to be quantized, we cannot actually talk meaningfully about notion of subsystems. And so back to our initial problem, when we're thinking about dualities, we could have thought that somehow the questions that we were addressing is like, how do we make sense of the box and what's inside of the box and so on and so forth. But really, in reality, the situation is much more dire in the case of when we think about gravity, because everything is coupled to gravity. And so we are all somehow experiencing right now the problem of how do we even define subsystems. And so technically, it is almost in the analogy as if we are inside the box ourselves. And so how do we even talk about anything really in a way that makes sense from this low energy quantum gravity perspective? Now, in a less metaphorical way, back to our description before in classical mechanics, the analogy, it is as if we are here, our understanding about low energy quantum gravity. We can talk about different systems which are, interacting gravitationally and quantum mechanically, but we're not able, as of now, to be able to connect that into a meaningful composition to talk about the joint system, and then to be able to see if we can actually have those notions of independence of subsystems that we had before. So that's why I think we should care about this, because I think it really, as I write here, flies in the face of fully funded, implemented, paradigmatic research programs, such as inflationary cosmology in the early universe, which relies on the formalism of low energy quantum gravity and propose a solution for the idea of how those different regions are in the CEB are somehow space-like separated, but nonetheless correlated. And the same goes for the current modelings of tabletop gravitationally induced entanglement experiments. And even more generally to the quantum reference frame program, those assumptions are also playing a role. Of course, as I said, the gravity is coupled, everything seems to couple with gravity. And so one can even beg the question, how does anything work? Why is it the case that nonetheless we're able to talk about subsystems in the lab in an independent fashion? So probably in the future, there's going to be a better understanding of how we can talk effectively about systems being independent, despite the low energy quantum gravity regime not allowing for that in general. Okay, so this brings us slowly to the final stretch of the talk. And the question is that all? Can we learn anything else by thinking about those insights. So let's go back to what people, the beginning of the quantum mechanics revolutions, we used to think about what was happening already in quantum mechanics. If you open Landman's book on Foundation of Quantum Theory, there's some very nice quotes. This is by Heisenberg. So he would say that Copenhagen interpretation of quantum theory starts from a paradox. An experiment in physics, whether to refer to the phenomena of daily life or to the atomic events, is to be described in terms of classical physics. The concepts of classical physics form the language by which we describe the arrangement of our experiments and state the results. We cannot and should not replace these concepts by any others. In a maybe more modern language, Landman himself, he says, the physically relevant aspects of the non-commutative operator algebras of quantum mechanical observables are only accessible through commutative algebras. Now, bringing this quote by Landman into our talk, it is as if what he's saying is that we are here. We are stuck at this level. Our observables, our experiments, our measurements, they're all classical systems, which are occupying, a region of phase space. All the data that we observe is actually classical data. And so all this structure that we think we have a handle on quantum mechanics and QFT is literally under the hood. And the question is, if really what we only have access here, should we really impose a lot of the structure that is present here on the lower levels or not? So the question that I ask is, why should we expect that the classically induced quantum factorizations should be preserved over time, including over measurements? Why should we expect that our notions coming from classical physics and from causality and macrocausality, as we reviewed before, should be the ones that are going to be fixing our lower levels, our quantum mechanical level, or quantum field theoretical level, or quantum gravity level? In particular, when we see that from the low energy quantum gravity point of view, we cannot even rely anymore on those different properties that we needed to define precisely the notion of different subsystems quantum mechanically. And this brings me to the last part of the talk, which is a sketch. It's not really a fully developed program at all. It's really an expectation maybe of what could unfold if we had a better grasp of quantum gravity, but is what I've been calling now with single world unitary quantum mechanics. So let's see why that could be the case and why it could, or how it could work out in the end. So as we quickly reviewed, the breakdown of microcausality in low energy quantum gravity, and therefore the subsequent laws of a well-defined tensor product structure basically undermines the concept of having gravitational quantum subsystems. And because this applies to anything, given that the gravity is universal, this breakdown of being able to talk about different subsystems is going to be present whenever physical description of anything really that we want to describe. And so I think that this may offer a new perspective on the measurement problem, that actually the idea of quantum subsystems is not to be considered to be invariant under measurements, nor generic Hamiltonian evolution, really. So basically different than classical subsystems, which are anchored in space-time and mostly preserved under time evolution, their quantum counterparts would actually move freely within the global Hilbert space. So the situation is, just to bring some analogy, it's kind of like similar to thinking about a macro state in thermodynamics, which is fixed from that particular resolution level where we have the thermodynamical observables. But of course, the microstate instantiating the macro state can be changing over time. And it's really our lack of resolution that we don't see what's the precise microstate. And we only rely on the fixed macro state in our description, but allowing the different microstates to play a role in the dynamics when we do statistical mechanics. So this is just to give some intuition about what I'm trying to say here. Okay, so let's now sketch what's needed to understand this. So let's fix a global finite-dimensional Hilbert space, just to simplify the problem. So we have some Hilbert space H. We have the algebra of bound observables defined on H, and some global Hamiltonian, and some initial pure state, rho 0. Then for each observable associated with our associated with the bound operators on the Hilbert space, we can compute the expectation value as we do. We can evolve the expectation value by evolving our state unitarily. And we know that for any fixed tau 0, and see that tau is my parameter that's actually defining the Hamiltonian evolution. And I don't want to call it T, and we can go back to that. We can talk more about that later. But I would argue that quantum mechanics is intrinsically background independent, and it's a mistake to associate the one parameter evolution coming from this inner automorphism of the Hilbert space to identify that with geometrical time. But that's just a side comment. We know that if you have the set of all the expectation values of all the observables at a given value of the parameter, in principle, you have all the data of the theory, because you know that the expectation value evolves deterministically, and you have all the whole empirical import of the theory. In particular, as we saw before, the tensor product structure, those maps that break down the Hilbert space into factors of Hilbert space, they are unitary maps. And so those expectation values, or the set of expectation values, are also invariant under this map. So we can actually break the Hilbert space into factors of Hilbert space by transforming both the operators, so going from global operators to local operators, and also by breaking down the state into states defined on each factor in Hilbert space. Now let's imagine, or let's consider that we want to describe our possible apparatuses that we have in the lab. So let's imagine we have a smaller subalgebra called app, which is part of the global algebra of the operators defining Hilbert space, which is really representing all the possible experimental devices that we have access to. And let's assume for now, at least, that our different apparatuses correspond to an independent quantum system. So we're relying on this idea that somehow, at least temporarily, microcausality holds, such that the algebra of the bound operators in Hilbert space is actually isomorphic to the product of the algebra acting only on the Hilbert space of the apparatus cross the Hilbert space of everything else. So I'm like really dividing my global Hilbert space between a given apparatus and everything else, including environment and the system I'm measuring. And needless to say that the dimensionality of the apparatus is going to be way smaller than everything else, arguably arbitrarily small. So this is good. We are now identifying what we mean by apparatus from the point of view of the whole Hilbert space. And by using now a particular tensor product structure that we just described, so we can factorize our Hilbert space between apparatus and everything else, we can go from our global observables associated with our apparatus to have actually local observables associated with apparatus tensored identity on everything else. And we can actually factorize arbitrarily the generic state in terms of a bipartite decomposition. It's just the Schmidt decomposition. Because it's only a bipartite system, we can always do that. And we can always write the global state as this particular state, such that we have a basis for the Hilbert space of the apparatus and a basis for everything else. By having this tensor product structure, the Hamiltonian also factorizes. So this is the most general Hamiltonian you can write. It's going to have some constant term over the whole global Hilbert space. There's going to be a free term for the apparatus, a free term for everything else, and all the possible different combination of operators that are interacting the apparatus and everything else. So what's crucial here is to realize that by thinking about the tensor product structure, you can also have a dual description in which you don't think about tensor product structure anymore, because you see that we went from global Hilbert space, observables, Hamiltonian, and state, to now having all these different coefficients. So we have this A0, AI, BJ, Cij, we have the PNs for the states. And so in fact, you can think about the tensor product structure as just by changing those coefficients. So you could fix the tensor product structure as you wish, and you just like now change the coefficients themselves. This is completely dual to actually having a different tensor product structure that would correspond to different systems. So there is a dual description between thinking about the tensor product structure or changing basically your whole kinematics and dynamics together. Kinematics here understood as a state, and dynamics understood as interactions that you have between the apparatus and everything else. So if you do that, now you can actually go back to what we had before. And we had these global invariants, which were the V, the expectation values of all the global observables associated with apparatuses, can be rewritten as a convex sum of actually the operators defined locally for the apparatus, not globally anymore. So everything we did so far here is completely standard. It's just a way, I'm just trying to spell out or lay down the framework to show what's going to change and how we can use the change of tensor product structure to make progress on the measurement problem.
And just for me to understand, Guilherme, may I ask a simple question? So what you do here is simply you take the partial trace of the environment.
Precisely.
And
So,
but it's correct. I mean that the time evolution does not preserve your tensor product structure because everything is mixed together, right?
Yeah. So far here, I'm actually keeping the tensor product structure fixed, and the time evolution would actually preserve it. The time evolution, of course, would change the correlation. It would change the amount of entanglement between the systems, for instance. And so forth. But the tensor product structure is completely fixed so far.
Okay, but the state, I mean, suppose you start with a state which is like a product state, then it will no longer be a product state.
Absolutely, yeah.
Okay.
For sure.
Good.
Okay. So now let's introduce three crucial assumptions that hints towards the existence of a new dynamical equation in quantum mechanics that would be responsible for the evolution of the tensor product structure itself. And I just want to acknowledge that in principle, my time is over. I think I can probably end in 5 minutes or so. But if I need to wrap up.
In principle, we have time until 4, sir. No worries.
So yeah, I should be done soon. Okay, so let's see what we want or what I would hope to happen, given our insights already from the discussion before in the talk. I want to have those three assumptions. First one is that when the size of the apparatus, the Hilbert space of the apparatus, is much smaller than everything else, and here actually is I mean, as I say, like it's arbitrarily small almost because we're really comparing everything else with a single apparatus, then there are many inequivalent tensor product structures which are available. In fact, they're all connected by global unitaries that in this particular case, I would even claim that we could imagine them to be connected in a continuous fashion. So instead of having just a single mapping tau, I'm going to think of tau as a function of the small tau, parameterizing how the tensor product structure changes over time. So again, going back to the dual picture in the Hamiltonian description, you could simply imagine that actually we are talking about those coefficients here, and we're evolving them over time. By evolving them over time, it's not only changing the state, which is what Felix was mentioning before, this Pn, but also changing all the interactions between the apparatus and everything else. This would be the analogous or the dual description of actually changing the tensor product structure itself. Second, there is a particular set. So now we have a trajectory of tensor product structures. In this trajectory, there is a particular set that I'm calling tau m, where something happens that actually the state of the system factorizes. And so we actually, whenever we hit a Tm tensor product structure, the whole state becomes basically factorizable between now the apparatus prime, because we're changing tensor product structure, so I mean another tensor product structure now, and everything else. So watch out that in the next formulas, whenever there is a prime, I'm actually going to another tensor product structure, which is inside the set Tm. And the third assumption is that due to violations of microcausality in quantum gravity, as we reviewed before, imposing a fixed TPS in any quantum gravitational system is just ill-posed and can only be seen as an approximation. So now I'm justifying why we change tensor product structure as we evolve over time. As the system evolves under the global Hamiltonian, the approximate tensor product structure changes continuously. I'm already relying on the first assumption and can be parameterized by tau of tau. And this can be understood, as I mentioned before, as actually our coefficients evolving over time, if you want. In particular, as I've been thinking more about this project recently, I finally realized that actually when you do effective field theory in quantum field theory, really changing the energy scale is the same as, of course, changing the coupling constants in the Hamiltonian for the interaction terms. So to some extent, the whole renormalization program, or the idea of changing your effective field theory by evolving towards different energy scales, also actually has a very close analog, if not actually being exactly the same as what I'm describing here. The fact that implicitly what's happening is that you're changing your understanding of what you call, an electron, a positron, and so on and so forth, depending on the energy scale that you are operating at. Anyways, putting together those three assumptions, we can arrive at a conclusion that actually what we understand as single outcomes in any measurement corresponds to a composition of a change of tensor product structure together with a local unitary transformation of the local algebra assigned to a given apparatus. And once we have those three assumptions, to show this is trivial. I can do that in one slide, because once you have now a tensor product structure that is inside that set M, which I'm thinking about measurements, then your whole state now written in the tensor product structure prime factorizes between the apparatus and everything else. And then you can actually basically rotate your apparatus such that this superposition can be written as a single state from the point of view of the aligned apparatus, which crucially you don't know what it is. And once you do that and then you trace everything else, then you see that your global invariant that we had initially there, that was what we call the empirical import of the theory, is completely mapped identically to the single eigenstate that you would measure for the rotate apparatus in this new tensor product structure. And then there is no anymore convex sum of the different possible eigenvalues, so on and so forth. So by identifying the appropriate tensor product structure and locally aligning the apparatus, you would see that the local measurement outcomes are actually the global invariants that we start with. So in this context, we'd expect that the probabilistic nature of the theory would arise from our lack of knowledge about the specific set of unitaries required to reach this point, both in terms of finding out the tensor product structure, as well as what is actually the right basis that you have to make the measurement to have the single outcome that you have in any given measurement. Crucially here is that everything that we did was always unitary. And so therefore, that's why in principle, you are relating those global observables to local observables in a way that we don't have to invoke anything such as, many worlds, so on and so forth. And that's why I've been calling this single world unitary quantum mechanics. Now, it's time to slowly wind down. And before we do that, how crazy is this? Like, are we doing something that's completely out of our minds? Or is there some connection with something that we actually know in general? And so we can do a quick comparison to GR, actually. What happens in GR? When we're moving through space-time and we want to compare measurements at different points along our trajectory, basically we have to update our inertial coordinate frame, our tetrads, so we can compare meaningfully different measurements we make. And there as well, we have three different steps that implicitly we consider. First, we have to solve Einstein's equation to find out what's the space-time metric. And despite the equations being local, they often require some global boundary conditions for a solution. So this is the analog of our to-be-found equation that describes how the tensor product structure is changing over time that we don't have right now. Once we do find the metric, then we can establish the family of local inertial frames using the metric. So of course, for any given metric at any given space-time point, there is many different there are many different possible tetrads that you can use. But then you have to find out what's the tetrad that you have to assign to yourself to actually meaningfully talk about measurements that you can make. And so basically you have to align the time-like tetrad with the observers for velocity, which is actually a purely local process because you make some measurements around you, and you define what's your forward velocity in relation to other reference objects. And then you can now assign the different tetrads for you and for everyone else to consider how you can actually relate you with anything else and make spatial-temporal measurements. In fact, if you do not align your tetrad with your particular forward velocity, it is as if you are thinking or computing or having measurements from a boosted frame point of view. And so, of course, you wouldn't be making the correct measurements and comparisons. And it's kind of the same as what's happening from this point of view in the measurement problem. It is almost as if we are not aligning correctly our observables, but also we don't have the tensor product structure correct because we impose it to be the same under Hamiltonian evolution, or we impose the tensor product structure to be the same under measurements, before and after a measurement. In this analogy, it would be the same as I just define my tetrad frame and I make a measurement of something, and then I move on my geodesic and I keep using the same tetrad that I had before to now make a new measurement and compare, for instance, the distance between those two space-time events. That would be incorrect. We would actually get to the wrong result. And so from this point of view, in terms of the analogy, we do something quite similar already when we think about GR. And from this point of view, basically what we would be missing is to identify or find out what would be the equation, ruling how the notion of, assigning coordinates in Hilbert space, which is another way of saying how we factorize the Hilbert space, has to be made into something more dynamical that we can actually go back and establish for any given point of the evolution of the system. And so to conclude, I just want to highlight that we know that progress is typically made when obvious notions are put into question. In particular here, we're thinking about notion of systems and subsystems. This happened in the past, both in terms of thinking about how to make simultaneous measures, temporally speaking, and that led to special and then later general relativity. Similarly with Planck, trying to really scrutinize the nature of radiation and being able to postulate that actually had to be some quantization of it. And I think nowadays there is a lot of emphasis on the idea of how to think about physical systems. And I do believe that there is a lot of synergy between thinking about this from the point of view of quantum gravity, and that may have direct consequences on the very understanding of what we mean by measurements in general. And I'm a bit over time, so I apologize for that, but thank you very much.
Thank you for this talk. Actually, the time is fine. We have in principle until 4, so we have at least still some time to discuss. So, are there any questions?
First of all, maybe I turn off the recording, right? I mean, then we are free here to discuss.
Yes.